Let's look at weak base equilibrium.
Weak bases behave similar to acids, to weak acids, but of course, bases are proton acceptors. So here we have ammonia, which is a common base. It's going to accept one of the hydrogens off of water, and we're going to form a conjugate conjugate acid right here. And then we're left with our conjugate base, which is our hydroxide ion. So bases always form hydroxide ion that come off of water, and the remaining ion is our conjugate acid. If you want to use a short form for this, we tend to use B to represent our base. We always have water present. And then again, that base is going to accept a hydrogen. So we end up with B with a hydrogen ion that is positively charged. And then what's left of that water molecule is the hydroxide ion. Similar to acids, this should be a liquid. Water is a liquid. And as a result, we don't see water in the ice chart. We see it in the ice chart, but we don't see it in the equilibrium expression. So once we set up our equilibrium expression, we change the KEQ to a KB to reflect the fact that we are dealing with a weak base. Here are your products. There's your reactant minus the water molecule. And then you can go and solve for whatever it is that it asks. So let's calculate the pH of a 0.1 molar solution of hydrazine. So hydrazine is a weak base. A lot of times in weak base equilibria, we will be dealing with organic bases. So they're not going to have hydroxide ions. They're not going to have oxide ions. They're going to be organic bases. So hydrazine would be classed as that. So we'll take hydrazine and we're going to interact it with water, right? Water has this slight dissociation to itself, and it contributes either a hydrogen ion or a hydroxide ion to the solution. Bases are proton acceptors, so that hydrazine molecule is going to gain an extra hydrogen. This is why we see the total go up to 5. And then what is left over off of that water molecule is the hydroxide ion that causes the whole solution to become basic. We need an initial concentration, which we have, change in an equilibrium. So the initial concentration is 0.100 molar. We're not worrying about water. It still doesn't change. We have no initial concentrations of our products. Over time, that reactant molecule will go down in concentration as it creates products. So our products go up by X. Weak base equilibrium is just like weak acid. They change by one hydrogen only. And so we'll never see any coefficients in weak acid or weak base. If it's a strong acid or a strong base, sometimes we'll see coefficients. So we're going to have 0.100 minus X at equilibrium, and then we'll have X and X listed there. So let's set up our KB expression. So again, number our steps here. Let's set up a KB because this is a base. And we're going to set it up. So we have our conjugate acid, so N2H5 plus times the hydroxide ion. Please put the charges in. Okay, they are ions. You need to indicate that. And then we divide by our base molecule, which is that hydrazine. So again, they're not going to give you the KB unless it's some, obscure acid or base that won't be in the chart. But off you go to page 6 of your data booklet, and you'll see a little chart at the bottom, which is your KB values for bases. And you'll find hydrazine there with a KB of 1.3 times 10 to the negative 4. So we're going to take that and we're going to have X times X in my numerator. We're going to divide by 0.1 minus X. We'll worry about sig figs later. And I would always be checking for small k. Okay, I know 10 to the negative 4, you might be like, I'm not sure, but why not? Let's check. Okay, so we're going to come up over here because I'm running out of room. And we're going to take 0.1, which is my initial concentration. We're going to divide by 1.3 times 10 to the negative 4. And I'm getting around like 770 or so, which is greater than 500, but not by a whole lot. So there are times with weak acids and weak bases, you might have to do the quadratic equation. Okay, you just be forewarned. If it's not greater than 500, you'll have to. But here it is. We'll take it, and we're going to neglect that x term, which will make our math a lot nicer. So we're going to get rid of that. Bring it over here. So I'm going to take 1.3 times 10 to the negative 4. I'm going to multiply that by 0.1. That is equal to x squared. My x value works out to be 3.6 times 10 to the negative 3 moles per liter. Now, they're asking us for the pH of the solution. So don't forget what this x value means. So the x value is here for my conjugate acid, but I don't really care about that. I care about this, the hydroxide ion. So I actually cannot calculate pH right away. I have to first calculate, so step 3, I have to first calculate pOH because I have the hydroxide ion concentration. So we're going to take negative log of the hydroxide ion concentration, which is just X. And that's going to give me a pOH of 2.44. We're going to subtract that off of 14, and we're going to get a pH value of 11.56. And there you go. Another example showing you weak base equilibrium.